Hello, geometry. Welcome to lesson 12.4 on probability distributions. So we're going to talk about what makes a probability distribution. We're also going to talk about what's called binomial distributions. Okay, so let's get right to it. Example 1, it says develop a theoretical probability distribution. So it says Teo and Henry are running for president and student council. You will select a campaign button at random from the box containing 3 for Teo and 3 for Henry. You will record the number of Teo buttons that you get. What is the theoretical probability distribution for a sample space of 0 and 1? Okay, so first of all, let's talk about what this means. So 0 and 1 represent each person. So say we let 0 be Henry's buttons, and say we let 1 be Teo's buttons, right? So a probability distribution assigns a probability to each outcome in the sample space. So for instance, there are 2 outcomes, right? So you can either get Teo's buttons, right, which would be the probability of getting a 1. And if I reach in randomly, there are 3 Teo buttons out of 6 total. That's 1/2 or 0.5. So the probability of getting a 1 in this situation, because we're going to use this as our sample space, is going to be 1/2. Same thing for Henry, right? So Henry is the probability of getting a 0. And again, it doesn't matter if I let Teo be 1 or 0 and Henry be 1 or 0, just one's 1, one's the other. Again, still 3 Henrys out of 6, which is 1/2. So the probability of getting a 0 is 1/2. And this would be your probability distribution. Typically, you list the sample space, and then you list out the individual probabilities for each of the outcomes, right? This is an example of a uniform probability distribution. It is uniform because the probabilities are equal, right? Same probability to each outcome. So if I scroll this up, same probability to each outcome. And typically, if you flip a coin, if you roll the die, a lot of times the probability distribution is uniform. Okay. All right, so there's our first example for probability distributions. All right, next. Okay, so B. It says now you plan to select a button at random, put it back in the box, and select another button at random. You will record the total number of times you get a Teo button for this experiment. So now you're just focusing on Teo. To find the theoretical probability distribution of the sample space is 0, 1, or 2. So 0 Teo buttons, 1 Teo button, or 2 Teo buttons. How does this probability distribution differ from part A? So now we're going to use a tree diagram to set up this distribution, right? So remember, a tree diagram is a great way to model visually what's happening. So because we are selecting 2 buttons, right? So here's my little starting point. So we're going to come here and here, right? So this is the first pick. And with the first pick, you either get a Teo button or you get a Henry button. So this is your first pick, right? And again, there is a 3 out of 6 chance to get a Teo button, which is 1/2. Again, a 3 out of 6 chance to get a Henry button, which is 1/2. And then you put it back, right? So which ensures independence. So now for the second pick, after you pick Teo, you could get another Teo button, or you can get a Henry button. And after you pick the first pick, and if it's a Henry button, you could then get a Teo button or another Henry button, right? And this represents our second pick. Okay, so now again, because the probabilities are not changed because you put it back, there is still a 1/2 probability of getting each of the Teo or Henry for the second choice. 1/2 and 1/2. Okay, and now we're looking for what is our outcomes, right? So 0 Teos, 1 Teos, or 2 Teos. So the probability of getting a 0, right, would be getting no Teos, which would be getting a Henry and a Henry. And that is this branch right here, Henry and Henry. You would just multiply 1/2 times 1/2. And that's 1/4. Okay. Now the probability of a 1, so the probability of getting a 1 would be the probability of getting Teo first and then Henry. It would also be the probability of getting a Henry then a Teo. So we're going to add this to the probability of getting a Henry and then a Teo, right? So here the order matters, all right? So the probability of getting a Teo or a Henry, or Teo and then a Henry, would be this route, which again is 1/2 times 1/2. the probability of getting a Henry and then a Teo would be this route and then this route. So that again is 1/2 times 1/2. So this is 1/4 plus 1/4, which would be 2/4. So this is 1/4 plus 1/4, which is 2/4, which is 1/2. So there's the probability of getting a 1. And then I'll change the green. The probability of getting a 2 would be the probability of getting a Teo and a Teo. That would be this path, Teo and a Teo, which is 1/2 times 1/2. And that would be 1/4. So your probability distribution here, and I'll do it in purple, would be, so the probability of getting a 0 is a 1/4 of getting no Teos. The probability of getting a 1 Teo is 1/2. And the probability of getting both Teos is 1/4. And this would be your probability distribution with that sample space and this probabilities listed out. And notice here that you don't have the same probability of getting each outcome. So this would be an example of one that's not uniform. So there you go. Okay, last but not least here on this video, example 2. It says develop an experimental probability distribution. So those are all theoretical, right? Because we didn't actually run trials. Well, now we're going to do experiments. We're going to actually run trials. So a cell phone company surveyed 500 households. So we looked at 500 people. That's our sample size, right? And we asked how many smartphones they have in their house, right? So we have 0, 1, 2, 3, 4, 5, or 6 or more. So that's the number of cell phones being your smartphones. And then again, this is your frequency, right? So this number should add up to 500. Okay? So it says, would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? So individuals would be, of course, the 1, right? Would be this. And then families of 3 or more, so 3 or more would be here, right? This chunk. So what we're going to look here, we're going to look at one probability compared to 3 together, okay? So what I want to do here is I want to find what are called relative frequencies, right? When your frequency numbers are different, right? When your sample sizes are all different, you should look at it out of the total. So let's look at some relative frequencies. So we're just going to extend this table down, and we're going to make a relative frequency row. And to find a relative frequency, we're just going to divide by the total. So this would be 10 divided by 500, and I've done all these ahead of time. It's going to be 2%. I'm going to do it in percentages, right? And we would do 66 divided by 500. This is roughly 13.2%. And then we do 120 divided by 500. This is 24%. And then we do 144 divided by 500. That's 28.8%. And then we do 79 divided by 500, about 15.8%. And then we do 37 divided by 500, and that's about 7.4%. And then we're going to do 44 divided by 500, and that's about 8.8%. Okay. Now I am going to make a probability distribution bar chart right here. So we're going to do a bar chart. So this is a way to visually represent our data. That says chart pretty terribly. Let me read that. So bar chart. And again, the reason I do this is because you might see this on your assignment today. So here's my bar chart. So here's my L-shaped graph. Now over here is going to be the percent, right? Our relative frequencies. That is also going to be your probability. So when you find the relative frequency, it is your experimental probability, right? So I'm going to put that right here, probability. Now when you do probabilities, you can write them as decimals or percentages. So we're going to use the percentage today. Notice that my highest number is 28.8. So I'm going to start at 0% and go up to 30 by 10. So 10, 20, 30. So there's 10%, 20%, and 30%. And I'll put the little dashes in between for my 5s. Okay? And now here, I need to have 1, 2, 3, 4, 5, 6, 7 bars, right? So I'm going to put a little dash for each one. 1, 2, 3, 4, 5, 6, 7. Right? And this is my number of smartphones. So smartphones per household. Okay? And that'd be 0, 1, 2, 3, 4, 5, and then 6 or more. Right? That's the 6 or more. Okay, so I'm going to make these bars. They're not going to touch. This is not a histogram. They're going to have some space between. And I'm just going to go up to each percentage. So 0 is 2%, right? So a very small amount of people don't have any cell phones at their house. Okay, so there's that bar. And then we have 1, which is 13.2. So halfway between 10 and 15. So here is the bar for 1. And then 2, again, keep a little space in between. 2 is 24. So 24 is a little bit below 25. And again, you want to try to maintain the same space, the same width for each bar. Again, it's hard sometimes on this pad. 3 is 28.8, so that's the highest, right? So that's almost 30. And then 4 is 15.8, so just a little bit above 15. So I'll probably just do 15, right? It's close enough. And then 5 is 7.4, which is halfway between 5 and 10 almost. And then 6 or more is 8.8, so actually a little bit above that last one. That's kind of an interesting, little bump up there, but there you go. Okay? So now the idea is, right, we want to compare the individual, so this column, which was 13.2%, to the families with 3 or more. And if you look here, 3 or more are these 4 stacks. So we're actually going to combine those 4 probabilities. So 28.8 plus 15.8 plus 7.4 plus 8.8. And that total percentage is roughly 60.8%. And of course, that is way higher than 13.2. So yes, of course, I would recommend families of 3 or more. So plans for families of 3 or more. Definitely. Okay. So again, this is how you build an experimental probability, and this is a way to create a probability distribution using a bar chart. All right. Great. Okay, so the next video is going to focus on binomial experiments, binomial distributions.